Section 4.10, Antiderivatives. So we kind of turn our attention to the inverse operation of differentiation. So a function capital F is an antiderivative of the function f if the derivative f prime of that capital F is equal to lowercase f of x for all x in that domain. So we're looking for the function that we could take the derivative of to get our function. So the general form of an antiderivative is going to be this, f of x plus c. f of x plus c. Because the fact is, there is not just one antiderivative. There are an infinite number of them, all differing by a constant. So let's just go ahead and look at part A on example 1. For each of the following functions, find all antiderivatives. Well, the function that I could take the derivative of to get 3x squared would be x cubed. Go ahead and take the derivative of that. That's 3x to the 3 minus 1, or 2. Okay, well, that's one example. What about x cubed plus 3? The derivative of that is 3x squared as well. So there is a family of functions. So what we'll go ahead and do when we say find all antiderivatives is put a plus c there, plus some constant, because the derivative of a constant is just 0. All right, part B, f of x equals 1 over x. Well, the integral, or the, we're going to use that term later, the function ln x would be a derivative of 1 over x, so that'll work. So ln x plus c. Now there is this stipulation that it's all x, which means to account for negative values of x, we need to say the natural log of the absolute value of x. And if you look at an integral table, you will see that it always shows ln of absolute value of x. What could we take the derivative of to get cosine? If we think for a little while, that would be sine x. So sine x plus c is our capital F there. And then last on this question, e to the x. Well, e to the x is the only function that is its own derivative and its own antiderivative for that reason. So e to the x plus c. Now, the indefinite integral, we're not going to use it quite yet, but the indefinite integral is basically comes down to notation. It's denoted, the integral, this elongated s of f of x dx. Now, this is going to be the most general antiderivative. That is the cap fx plus c. Okay? So this is actually finding a family of antiderivatives. Okay. Now, we call the expression f of x the integrand. Our integrand. X is our variable of integration. Dx is the differential, which we've seen before. And then, well, that's everything we need to know right there. Now, we do have a theorem here that is the power rule for integrals. The integral of x to the n dx is x to the n plus 1 over n plus 1 plus c for n not equal to negative 1. So if n is negative 1, that's actually the natural log of x. So this is the inverse power rule from our differentiation. Okay, those two are tying together. So we're going to use that in just a moment. But for each of these following statements, verify that the statement's correct. Okay, so here is our cap f of x. We need to verify that the derivative of cap f of x is, in fact, this f of x. All right, so f prime of x, capital F there, is 2x plus e to the x, and we'll take the derivative of that, so that is gone there. Okay, well, that is not correct. Okay, so this statement here is not correct. Now, what we could do is we could say over 2, that would fix it. That would fix it. So let's go ahead and say that capital F of x should be x squared over 2 plus e to the x plus c. That's what it should have been. That's what it should have been. So not the antiderivative. Derivative. Now, it's not the antiderivative because if we take the derivative of that antiderivative, we should get our function back. All right, part B, x e to the x dx. So is this capital F of x is the integral of that f prime of x, or f of x. Let's just take off the prime. We're actually going to take the derivative over here. All right, so f prime of x, we're going to have to use the product rule here. So this will be x, the derivative of, actually we'll take the derivative of x first. So that's 1 e to the x plus x. The derivative of e to the x is e to the x minus e to the x. And combining terms, we get x e to the x. So yes, this is a correct statement. It's a correct statement. Okay. Our next theorem is two ideas together. Let capital F and capital G be antiderivatives of lowercase f and g respectively, and let k be a real number. We have this one idea that is the sums and differences. If you take, so we could say there, then that is true, and that is true. Okay. So if you have the integral of f of x plus g of x, that's going to be the antiderivative of each separately. And if it's plus or minus, we just kind of carry that down. Also, if we have a constant multiple, and this will come in handy, if we have a constant multiple, we can factor it out of the antiderivative. All right, let's kind of jump into some more examples. Evaluate each of the following indefinite integrals. Well, based off our power rule, we can evaluate each of these separately. So 5x cubed, we'll keep the 5. In fact, let me do this. Ignore the 5 and take the antiderivative of x cubed, which is x to the 4th over 4 based on our power rule, minus 7 times, and that will be x cubed over 3 from x squared, plus 3. We're ignoring those constants that are in there. So that will be an x squared over 2 plus 4 times, in the integral of nothing, we just get an x in there, plus c. So this is 5/4 x to the 4th minus 7/3 x cubed plus 3/2 x squared plus 4x plus c. That is our general antiderivative of that polynomial function with those pieces in there. All right, part B does not look like the other problems. However, if we can rewrite this as, we'll divide the x in, so that's x plus 4x to the negative 2/3, so that's 1/3 minus 1. All right, dx, I'm going to go ahead and group all this together. Now, based off our power rule, the first bit is x squared over 2. Now, this power rule works regardless of the exponent, okay? As long as it's not negative 1, because we're dividing by 0 then, it works for every exponent. So we could write this as plus 4 x to the, add 1 to that. So that is 1/3 divided by 1/3. So writing that a little bit clearer, x squared over 2 plus 12x to the 1/3. And I'll go ahead and write that as a cube root plus c. Okay. Now this next one doesn't apply the power rule. It actually requires us to look at a table of integrals. Now, in the textbook, in OpenStax Calculus Volume 1, in this section there is a list of some common integrals. And one of those shows that the integral of, or the antiderivative of 1 over 1 plus x squared dx is tangent inverse x plus c. So in our case, we have a constant multiple of 4. So this is going to be 4, and then the antiderivative of the 1 over 1 plus x squared portion of that is the tangent inverse of x plus c. We just have a constant of 4 floating around there. Okay. Part D, the antiderivative of tangent x times cosine x. Okay, well, this doesn't look like anything else either. So I'm going to first write this as sine x over cosine x times cosine x, which reduces down to the antiderivative of sine x dx. Well, we know that the antiderivative of sine is a negative cosine, so negative cosine x plus c. Okay, moving on. We've got one of the last things we have in this section. Sometimes we're interested in determining whether a particular solution curve passes through a certain point, x naught, y naught, and that is y of x naught equals y naught. So our input is the x naught. It's our initial condition is what this is called, and our output is the y naught. So the problem of finding a function y that satisfies the differential equation dy over dx equals f of x with the additional condition that y of x naught equals y naught is an example of an initial value problem. And so what that point is our initial condition. All right, now let's work with this. dy dx equals sine x sine x. So let's just work with that. So if the derivative of y is sine, what we really need to do, let's go ahead and rearrange this first. dy equals sine x dx. What we really need to do is find the antiderivative of both sides of this equation. Well, this is y equals, and we just found the antiderivative of sine x was negative cosine x plus c. We found what y is. Now, the general antiderivative of y is negative cosine x plus c. However, we have this point, this initial condition. So let's evaluate in that function plus c. If we evaluate this at 0, so this means y is 5 and x is now going to be 0. Well, cosine of 0 is 1, so this is negative 1 plus c equals 5, which means c is 6. So our particular solution, okay, we had our general solution here. Our particular solution is y equals negative cosine x plus 6. That curve will pass through the solution 0, 5. All right, next we have solve this initial value problem. Okay, so again, if you notice, we're just going to take the antiderivative of this function here. So that will tell us that y equals 3, and then x to the negative 1 divided by negative 1 from our power rule, plus c. So y equals negative 3 over x plus c. So if we use our initial condition, that is 2 equals negative 3 over 1 plus c, which shows that c is 5. So our particular solution, again, our general solution is here, but our particular solution is negative 3 over x plus 5. All right, our last example, we'll talk about some acceleration and braking distance. So a car is traveling at a rate of 88 feet per second. Okay, that is 60 miles per hour when the brakes are applied. The car begins decelerating at a constant rate of 15 feet per second squared. How many seconds elapse before the car stops? And then, how far does the car travel during that time? Okay, so to begin, let's look at how many seconds elapse before the car stops. So what we do know, there's not very much we know, but we do know that it is it's decelerating at a rate of 15 feet per second squared. So this means our function a of t, our acceleration function, is negative 15 feet per second squared. Well, that means if we take the antiderivative of this, this will tell us our velocity. Our velocity function is negative 15t plus c. If we knew an initial condition, we could find the exact velocity, and we do. Velocity at time 0 is 88 feet per second. 88 feet per second. So evaluating that at 0, 88 equals negative 15, 0 plus c. So that means that c is 88, and our particular solution there is negative 15t plus 88. So how long does it take before it stops? Well, that would be a question of when is velocity 0. So negative 15t plus 88 equals 0. And solving that, we get 88 over 15. So the time is 88 over 15 seconds. That is how many seconds elapse before the velocity comes to a 0, comes to a stop. Okay, now to find how far the car travels during this time, we need to know the position after those 88/15 seconds. Okay, we need to know when it's going to stop. So we're going to go ahead and say that the initial position is going to be 0. Okay, so let's go ahead and say this. If v of t equals negative 15 t plus 88, well then that means, taking the antiderivative here, negative 15 over 2 t squared plus 88 t plus c. So let's go ahead and say the position, at time 0, we'll just call it 0, which means that our particular solution is negative 15 over 2 t squared plus 88t. All right. Well, so the position, how far it got after 88/15 of a second, would be s of 88/15. 88/15 squared plus 88 times 88 over 15. And this is going to be approximately 258.133 feet. So that is the distance it traveled from 0. So assuming it started at a point of 0 and going 88/15 of a second, based on its current velocity, we know that is the distance that it traveled. So there we are. That is the end of section 4.10. Here's our great introduction to integration and antiderivatives.